We begin our tour of data analysis by stepping away from the Philippines for the moment and into the watershed I know most intimately. It is home to most of Washington, D.C., and I have lived here much of my adult life. Using the D.C. watershed as an example, I want to discuss a concept I call data space, what it is and how we can use it to mine valuable information. This example focuses on the environment, but the concepts are equally applicable to business, to sports, to public health, or any domain that would benefit from data analysis. These concepts are foundational. They form the backbone of our entire course. For your frame of reference, the Capitol, where the U.S. legislature convenes, is right here. And here's a picture of the Capitol I took earlier this year. 5 miles northeast of the Capitol is the watershed's monitoring station in an area that looks like this. Let's drill down even further to a single drop of a water sample I took last summer. As you see, there's a great deal of variety and number of different algae in just a single drop. Too much algae causes problems because when algae dies and decomposes, it uses up oxygen, which, as this article from the Washington Post points out, can wipe out all the fish in an area. Researchers have collected a lot of data from this station, a few of which are listed here. Algae contains chlorophyll A, which helps them photosynthesize. Chlorophyll A is therefore used to track how much algae there is in a body of water. In this example, we will investigate the relationship among chlorophyll A, nitrate, and ammonium. Measurements don't exist in a vacuum, and it is important to describe the context, such as the time and place where our measurements were taken. If we're lucky, we also have information about what I call context attributes. These describe something about the context in which we took our measurements. For example, based on satellite images, we have information about how land is used in the Washington, D.C. watershed. Based on this information, we can conclude that land in the watershed is highly developed. When I use the term data space in this course, I refer to data on measurements or categories such as, is the watershed good or bad, the context for these measurements and categories, and information on context attributes. But this is just one watershed of the many watersheds that influence the Chesapeake Bay, the largest estuary in the United States. To investigate water quality in this bay, I have put together a data set of almost 17,000 observations covering 10 years in 156 watersheds and 261 monitoring stations. If we define big data in terms of volume alone, this is not quite big data, but I prefer to think of big data not just in terms of volume, but also in terms of recognizing the real world, in which data must be gathered from different sources and from different levels of resolution. And we must be able to account for and to analyze these data despite their inherent variability. In this course, we do this by looking at the probabilistic relationships residing within our data space. For example, I often start a data project by visualizing how the data look by counting. Here are 6 observations from my data space. In this table, I have concentrations of chlorophyll A along with their context. Some concentration values are negative because they are presented on a logarithmic scale. Let's count the number of observations corresponding to each value of chlorophyll A. The first observation was taken from this watershed and has a chlorophyll A value of 1.42, which is roughly here. The next 2 observations have a value of 0.73. The next 3 observations have a value of minus 0.66. Let's cue in the music as we continue our count across all 17,000 observations, across all watersheds, and across all years. Consider a chlorophyll A value of 3 milligrams per liter. What is the probability that the randomly chosen observation has this value? Well, what is the probability that I draw a king from a deck of cards? There are 4 kings out of 52 cards, so the probability of drawing a king is 4 over 52 or 1 over 13. Similarly, there are 671 observations with a chlorophyll A value of 3. Dividing this by the number of total observations yields a probability of 0.04. Doing this for all values of chlorophyll A across all observations, we can plot the probability of each value. We call this plot a probability distribution. For modelers, probability distributions are exciting to behold because it suggests we are studying a system influenced by both order and randomness. If we are smart and lucky, we can develop a computational model describing this system. Let's first see how we model the system's order. To do this, we try to explain the variable we're interested in this case chlorophyll A, which we call the response variable, in terms of a second variable called the predictor, which in this case is the ratio between nitrate and ammonium concentrations, or the N ratio for short. For the first observation, the N ratio has a value of 2.26, corresponding to a chlorophyll A value of 1.42. We do the same thing for the next 5 observations. In fact, we'll do the same thing for all observations across all watersheds across all years. This allows us to approximate the line describing the relationship between the N ratio and chlorophyll A. As you see, this relationship is negative. The higher the N ratio, the lower the chlorophyll A. We now shift our attention to modeling the inherent randomness in the system. At an N ratio of 3, the predicted chlorophyll A value, as approximated by our line, is 1.6. But there are 37 observations with an N ratio of 3, and most of them do not fall on the line. Let's focus our attention on one of them, which is an actual chlorophyll A value of 3.4. We assume that the actual deviates from the predicted value because of inherent randomness, and their difference is called the residual, which in this case is equal to 1.8. If we took all 37 observations where the N ratio equals 3, we could derive the residual for all of them. Plotting these residuals in a similar way to how we earlier plotted the probability of chlorophyll A concentrations, we derive this Gaussian distribution, also called the normal distribution or a bell curve. This distribution of residuals holds true for all the points on our line. This course's first major theme is that we can, by relying on certain assumptions, approximate a mathematical description of the system we are interested in that captures both the order and randomness in our data. The second major theme is that context matters. We want to go beyond general patterns and investigate why a particular place or group or school or company division might differ from the general population. For example, returning to our Washington, D.C. watershed, we see that it generates about 100 of our 17,000 observations. If we were to develop a model based solely on the Washington, D.C. observations, we would come up with a slightly different model, one in which the relationship between the N ratio and chlorophyll A is even more negative. To repeat, what is data space? It is data on measurements, such as chlorophyll A and the N ratio, and the context, such as place and time, in which the measurements were made. It also includes information on context attributes. For example, in the Chesapeake Bay project I'm working on, I have quite a bit of data on land use taken from satellite images. I also have data on the stream density within each watershed, as well as their average elevation above sea level. How do we use data space? We use it to investigate probabilistic relationships among measurements or categories, context, and context attributes. Exploring our data space, we may, as we have already seen, estimate a model approximating the data across all of our observations. We may also carve out some data to focus more narrowly on particular contexts. For example, by allowing our model to vary by time and space, we can see how this relationship between the N ratio in chlorophyll A varies between, say, Glen Echo in Maryland and Jamestown in Virginia, and in winter and summer. Our model shows that during winter, this relationship is negative in Glen Echo and positive in Jamestown. It also shows that in Glen Echo, this relationship differs between the winter and summer months. We may even be able to explain these different patterns on the basis of context attributes. Here is a graph of elevation levels in Glen Echo and Jamestown. Glen Echo has generally higher elevations than Jamestown, prompting us to ask, might the different elevation levels in the two watersheds explain the patterns of N ratio and chlorophyll A relationships? To summarize, data space can explain the order and randomness in the system we are interested in, while accounting for differences in context. We can slice and dice data space and ask a series of questions. Do the data follow a probability distribution? Can the order and randomness in the distribution be modeled, while also accounting for contextual variability? In other words, is there a global pattern to explain our system? And can we also understand the complexity behind this pattern by accounting for contextual variability? Finally, here is the Chesapeake Bay, reminding us of nature's grandeur and beauty. The physicist Werner Heisenberg reminds us that what we observe is not nature, but nature exposed to our method of questioning. This quotation fills me with both humility and gratitude. On the one hand, it is humbling to think we can only grasp nature's essence to the extent that she is willing to share it with us through our faulty observations. On the other hand, through the tools we will learn in this course, you and I have been granted the privilege of possibly glimpsing some of what is beautiful and still unknown in this wonderful world.